Okay, so our last talk of the session is by Pratik, and he's from Western University, and he's going to talk about molecular dynamic investigation of thermophysical and viscoelastic properties in two-stage thermosets.
So, hello everyone. I'm a graduate student at Dr. Deniston's lab at the University of Western Ontario. I'll be talking about the molecular dynamics investigation of thermophysical and viscoelastic properties in two-stage thermosets, in which I'll be covering two thermophysical properties, heat capacity and thermal conductivity, and a new theoretical framework for calculating viscoelasticity. So the question is, why simulate a Qing thermoset atomistically? We have also the coarse-grained models, but why we are doing at an atomic level? Thermosets are sort of a polymer which, once cured, they cannot be reversed, like a thermoplastic, which can be melted and reshaped. So small monomers react to actually lock into a permanent cross-linking network, which ultimately makes this material stiff and hard. Now, as the curing proceeds, the properties like stiffness and heat capacity keeps building up and keeps changing. And that depends on the degree of cure, not just the chemistry of it. So molecular dynamics lets us build the network bond by bond and check the properties at any stage of the curing process. The material system that we are using in this particular investigation is a commercial UPPH resin, which is nothing but unsaturated polyester polyurethane hybrid resin. It's a natural resin that we procured from the commercial companies who make it, and the ratios that you see here for the molecules are actually practically used at this point in time to manufacture these ones. In the simulation that we are running, we have around 14,000 atoms in our simulation box, and there are 4 key ingredients with different, basically these are like, one is the isocyanide cross-linker with different functionality, a polyol that also carries methacrylate vinyl groups, a styrene which is a co-monomer, and a peroxide inhibitor. The whole simulation is based on 2 stages of different reaction. One is the urethane bond, which forms the first, and then which is basically when isocyanide reacts with the hydroxyl group, and the radical chain which polymerizes the vinyl group. Now there are 2 stages of the curing chemistry. On the left hand side that you see here, basically on the left hand side is the curing mechanism. And panel A that you see on the top is the uncured mixture. This is where just these 2 liquids are mixed together and then let it settle down. And there are 4 components in that. One is an isocyanide, which is represented in red color, polyol in blue, styrene in gray, and peroxide in green. The panel B, this one, shows the state of urethane polyaddition. That's the first stage of the reaction, where the NCO groups react with the hydroxyl group and form the urethane linkage, and creating the new bonds that is basically between the isocyanide and the polyol molecules. And the panel C that you see over here is basically the fully cured state after the radical chain polymerization happened, and that's why you see these chains of polymers. And this is basically because of the peroxide inhibitors decomposes into the radical that ultimately attacks on the vinyl double bonds, weaving a dense cross-linked network for this one. On the right hand side, you see the 3 molecule types and their chemical structure in a coarse-grained model as a representation of PMDI isocyanide, an unsaturated polyester polyol with styrene comonomers and peroxide inhibitors. The key point here is that the urethane forms a sparse cross-link network between polyol chains, while the radical polymerization creates this dense network there. see in this one. And together, they determine the final thermal and the mechanical properties of the material. Now, before we start the reaction process, we need to first bring the system to the stage where it is ready for reaction. And the way we do that is by basically the few steps process. Here we first start with the most like a very expanded box, and we populate it with around 363 molecules in the ratios that I described before. And they are placed randomly at a very low density. We then randomize these molecular orientation at a high temperature, that is in the randomization process that you see here. And then we compress this box in a stepwise compression to an NPT ensemble. Same number of molecules at a constant pressure and a constant temperature. And that's the staircase process that you see in this one. Once you reach to a certain density, which is a little higher than the experimental value for this uncured polymer, we then equilibrate it for a very long duration in an NPT ensemble, where we keep a temperature of 290 Kelvin and measure keep the pressure at 1 atmosphere. The system equilibrates automatically, and the density comes back to the experimental value of around 1.08 grams per cc. Now, once we have the system equilibrated at that exact point that we want, we start with the reaction. Now, in this particular simulation, we are using the normal MD molecular dynamics force fields are fixed, which means that the bonds cannot be created or broken, but we still want the bonds to be occurring in the experiment. So what we do is we use a Arrhenius model here again. We look at the nearby reactive pairs and at every time step, and then against that we calculate the probability, which is based on the distance and the temperature. And if the pair passes the test, you form a bond, otherwise you don't. And this topology is updated in real time, so all the angles and the dihedrals are also updated as the reaction goes on. And the parameters for these angles and dihedrals come from the compass parameter that is in the LAMMPS. LAMMPS is the simulator that we are using in this case. And the simulation continues without any interruptions, without any reruns or restarts here. And this is important because it means the whole network here is self-consistent, and it grows self-consistently inside one continuous trajectory. And there are no artificial freezing happening, there is no minimization between the bond formations or anything. So it just keeps evolving, and we do not have to interrupt it. This is the full simulation pipeline for the entire process that I'm describing today. And it's bifurcated into 3 different stages: the construction and equilibration, curing, and property calculation. The construction phase that I mentioned before is basically the same one with the stepwise compression, equilibration, minimization, and then the curing process, where the first stage comes with the urethane reaction, and then the second stage is with the radical polymerization, and after that we calculate the properties, the thermophysical properties and the viscoelastic property. The values that you see here, U0, R0, is just a representation of the amount of curing that has happened. U0 means 0 urethane bonds are created and 0 radical bonds. U50, R0 is like 50% of the urethane has done and 0% of radical. However, the other one is the almost fully cured state. So, now how do we measure the thermophysical properties from this equilibrium molecular dynamics? So for the heat capacity, what we do is we look at the energy fluctuations happening, and we take the variance of it, and we get the heat capacity. This is the specific heat capacity, so you just divide it by the overall mass of the system. And for the thermal conductivity, we use a green co-correlation, where we look at the heat flux autocorrelation function by equilibrating the system with the NVT. Both the systems are equilibrated with the NVT ensemble, and then when they converge, we look at the average value of the heat flux in this case. Now, heat capacity in a little more detail. So we use a modified NVE plus Longinon thermostat to modulate the temperature in order to fluctuate the energy. The limit of 1 angstrom per time step is a stability safeguard, and the quadratic bond term encompasses 2 parameters that we are using. Also, we pre-equilibrated the state to 50 picoseconds with an NPT so that the system is at a certain minimized state where the energy fluctuations will not be extremely high, that will disturb the equilibrium and give us a false value for the heat capacity in this case. This particular calculations that we did, this is a preliminary result that we have at 293 Kelvin. For the uncured system, we expect the value to be around 2000 to 2300 joules. And those are the values that I'm getting for 293 and 313, which are a little off, but I guess because these systems, we need more replicas in order to get an actual value. So this one is just from one of those, and we are still running a few of these as we speak. For the thermal conductivity, we use a beam Kobu in practice. We look at the heat flux correlation functions and then we integrate it to converge. It is, we run this for a longer window, and the most important part is that initially you see the fluctuations at a very high rate, so you want to have a lesser time steps when you're doing it for, let's say, like 10 picoseconds, and then you can increase the time steps because the fluctuation kind of reduces. So you want to look at that, the autocorrelation that is happening as we go by. These are the primary results that we got from our analysis so far, and they do match typically to what we expect from the literature. And once again, we still need independent 5 to 10 replicas for this one too. Now, that was all about the thermophysical properties, but now what about the viscoelasticity? So viscoelasticity is a little bit of complicated stuff to calculate when it comes to molecular dynamics. As per the classical elasticity theory from Vaughan and Lane, we know that if you have a crystal and you put some shear force on one of the sides, the entire crystal, the atomic structure moves with the same strain that was applied. But for an amorphous system like the one that we have with the polymers, it's like, imagine a crowd and somebody just pushing somebody, one of the people. The distribution of the force is not systemic. There are some people who might constrain that, and some people might just push the extra force behind, and so and so. So the amount of force that is being pushed is not uniform. So that's what you see on the right hand side image over here. This is for the crystal, this is for the amorphous stuff. So we used something called as non-affine lattice dynamic approach, which was proposed by Professor Zakoun recently, actually in 2025, and that's the one we are going to go with in this case particularly. And what is this non-affine lattice dynamic approach? So we look at, it gives us a full spectrum of loss, storage and loss modulus, G and G prime and G double prime, which directly comes from the system's vibrational modes. There is no shear simulation needed in this case. The key ingredients are basically the mass-weighted Hessian matrix of the potential energy with respect to the displacement, which also gives us the eigenvalues for the vibrational frequency. And C of omega that you see here is a propagator built from these particular modes. The gamma tilde is the affine force field, which captures exactly the amount of force on each atom changes under the affine strain. Basically, the extra force that is being applied on each atom at this point. And GA modulus is nothing but the purely affine force modulus that we see, like in a crystal. So the correction of gamma tilde is being added into the GA in order to eliminate the affineness in the non-affine motion in this case. So the computational procedure that goes around calculating viscoelasticity using the NLAD process is firstly equally we minimize the curing snapshot, because now we have snapshot from each and every time step that we want. We first minimize the energy, because this is a temperature equals to 0 Kelvin reference. So we need to minimize it, and once we have that, we can calculate the dynamical matrix by finite displacement method, and we are doing this in labs. So this is a real value that I got for the configurations that I have, around 14 GBs. Each Hessian matrix was around 14 GBs. I'm still working on reducing the amount of this file size so that I can compute other things on top of that. The eigenvalue decomposition is later on done on this matrix using a GPU to identify low frequency responses. We don't need all of them. There are more than like 41,000 modes, but we don't need those. We just need the lowest 2,000 modes in this case. And once we have that, we look at the moduli and averaging them using the process that I mentioned just before. Once again, we still need more replicas in order to average out the values that we get from this as well. Now, what NLAD predicts from the queuing network? This is very interesting, because non-affine softening is a direct signature of how well connected the network is. This is something that you also can get from the graph theory values, but this is a secondary validation that we can get from it. Fewer mechanical constraint per atom means more non-affine motion and softer material. As the curing proceeds, we see the number of constraint per atom increases, because more cross-linking is happening. And as the theory predicts, that non-affine relaxation should decrease because of that. And the affine modulus should increase, and ultimately elastic plateau you will be seeing over there in G prime, and should sharpen as it strengthens. In short, NLAD gives us how the network is stiff enough, mode by mode, as the curing happens, and that is why molecular dynamics comes into the play, because you can take a snapshot of every curing stage, and you can look at like how the strengthening of the material is happening as the reaction goes by. And you get an entire vibrational spectrum, which can be later analyzed for various different things. Now, the study framework that we are looking into this is that there are 3 curing states as of now. One is the uncured, the urethane only, and the fully cured radical plus urethane at this point. And the goal is to have one consistent pipeline which connects the curing chemistry directly to the measurable macroscopic property. This is another thing why we are not going with the green-gold relationship for the viscoelasticity, because we want to have more of a macroscopic view on the viscoelasticity in this case. And then we measure these 3 properties as of now. In summary, the methodology side, the reactive molecular dynamics grows the urethane and radical network self-consistently, matching more curing kinetics that we get from the literature. The green Kobo and the energy fluctuation methods gives us the thermal conductivity and heat capacity respectively in thermodynamic sense, and the NLAD approach gives us the viscoelasticity values without any shear deformation happening. The next steps would be to have more replicas for heat capacity and thermal conductivity, and create a more clean pipeline at this point in time for this curing to reach at different states of the reaction, and also look at the NLAD spectrum to identify what values we get, and validate that through the DMA results experimentally. And these are the references. Thank you very much.
So questions for Pratik? Yes, please.
Thank you for the next presentation. So I wanted to understand more on practical application. Like, what is the practical application of your where you see that?
So what are the practical
in the physical world?
Yeah. So the end goal that we are reaching to with this experiment at this point is experimentally analyzing the network. The polymer network is very difficult. You always have the end state of the polymer. You don't see how the network is evolving and how the properties are building up. So using this kind of pipeline, you can actually see what bonds are responsible towards, let's say, the more efficient way of, or more faster the network is evolving, or the cross-linkers are forming. So basically, after this point, we are also going to look at like how we also have the atoms and the bonds data. So I know the entire graph of how the reaction is evolving. So I get the whole graph out of it, how the whole network. Using topology, I can identify what are the graphical properties within this particular network which is responsible towards building the heat capacity. Like for example, like if I see the heat capacity building up very quickly at the earlier stages of the reaction, what are the bonds that are creating that? And then, for example, if the hardening of the material, stiffness of the material is getting somewhere in the middle of it, we know what are the bonds which are responsible for that, and which will ultimately help chemists to synthesize more specific type of polymers. Like if you want something that is hard enough under a certain condition, so you want that kind of chemistry to work into that. I'm not a chemist, so I don't know a lot about that, but I can potentially help them with this idea of like, these are the bonds that you might want to focus on. These are the type of reactions that we want to see that will ultimately lead you to getting that kind of property.
So you can also maintain dynamic conditions during the reactions.
Yeah. So we can do a lot of alteration in mid-phase, which is one thing that I'm also designing in the pipeline, because you can just take one snapshot of it and do something else from that. Maybe you can add some other things into it and see how it reacts to that. So it's sort of like a virtual lab for polymers.
That's very cool.
Yeah.
Thank you.
Yes, please.
Can you actually reliably do that, what you just said you can do? Because in the end of the day, it's computational studies. And you're using, whether you use non-equilibrium molecular dynamics or whatever, but you still use molecular dynamics, meaning that you impose periodic boundary conditions, which is far away from any real polymers.
Yeah, you're right. I mean, I see the point. So what we did here was more of a reverse engineer technique. So which we didn't write in the paper, but we got all the information about the material, the ingredients, the ratio from the actual prospects that the company produces these in real life. So using those values, using the NMR spectrum that we got from there, we first created the system that will be most practically replicable in this case. And that is why we are confident with the values that we are getting, because they can be cross-verified with the ones that are being in the lab itself. So the only thing that what we are doing different is looking at a very atomic level, how these bonds are created, what is happening within the chemistry of it that is enabling the property to exhibit certain value.
Right. So at that scale, probably
yes,
it's going to be reliable.
Exactly, and that is also why I'm using the NLAD process, because with the green Cobu method, you still get a viscoelasticity, but the time scales are different. Like if you look at a very viscous liquid, within the atomic level, they might be moving very fast, but on a macroscopic level, it slides very slowly, and that's where the NLAD process comes into play. So,
Thank you.
If not, let us thank Pratik.